Okay, so after that mathematical interlude, we still continue our lecture. Um, this is the end of the slide from the lecture just before the mathematical interlude. In the discrete voxel representation, remember that we've now shown that this is how we set up our quantum field theory commutation relations. We say that the phi operator at voxel x comma the pi or the local momentum operator at voxel y, the commutator of those two things is equal to I Kronecker delta of x comma y. In the continuum representation, we have this. I mentioned that these commutation relations are some of the most important equations in all of QFT. Now, this is one of the most important parts of this course as well. These commutation relations, which we saw were just a very natural extension of single dimensional quantum mechanics to our quantum field theory, Hilbert space and operators. These commutation relations imply these commutation relations. Remember, we expanded phi and pi in terms of these A and A dagger operators. And if you assume these commutation relations, which were very naturally extended from quantum mechanics, that will imply these commutation relations for the A and A daggers. In particular, A non-daggered commuted with a dagger, P and Q, is equal to the Dirac delta, the Kronecker delta of P comma Q. And the AP, AQ is equal to 0, and A dagger P and A dagger Q commutators are equal to 0. And these are the discrete form taken also from Klauber. You could, I don't know if it's in textbooks that I've came across, but you could also imagine that if you stuck with the same Fourier convention as Tang, but did a discrete representation, you could also imagine that people could write this as well. Ultimately, the formulas, when we calculate things, should all be the same. So these are kind of conventions based on what book you're looking at, but these are the ones that Klauber uses. This is not 100% what he uses here. He uses a Dirac delta here, but we will just use the Kronecker delta, and based on some of the things we said before, this will work out exactly the same. So that you can prove this. You can prove this both ways. This is an if and only if. We're just going to kind of really only show it one way. You can look a little bit more carefully at the proof and probably not very hard to see how it goes both ways, but we're going to show that if these things are true, then these things are true. So we're going to show it one way. This is the continuous form of these same relations. That this, if you look at the lecture notes of David Tang in quantum field theory, this is what he has. And the slight difference is that he, because of the way the Fourier transform is defined in his notes, he has this factor of 2 pi to the third. And because it's continuous form, you have this Dirac delta instead of the Kronecker delta. And these commutation relations here are also defined in terms of the Dirac delta. The expansion of these will be in the Tang form in the continuous form. The expansion of these will be in the discrete form, as I'm just about to show. All right, so here's that proof, at least in one direction, or so I'll really call it a partial proof for the discrete form. Recall that we said that we can expand phi of x by assumption in this formula over here in terms of these A's and A daggers, exactly according to this formula taken from Klauber. We also said, but we didn't justify it, we can justify it later, that the pi of x, the local pi of x operator, can also be expanded like this in terms of the A's and A daggers. There's a minus sign here and a minus I and a couple of other little changes, but it can be expanded, and this is completely consistent with this. If these are the two expansions, and we assume the commutation relations that we said before, let's see what happens. Here's phi of x. Let's do the commutator of phi of x with pi of x. And I apologize, let's do the commutator of phi of x and pi of x and see if we expand these things into it, if we really get what we're supposed to get, I Kronecker delta x y, as the previous page showed. So let's see what happens. So here's my formula for the commutator of phi and pi. Now there's a lot of tedious math, and you just basically have to follow it, and there's some interesting subtle things. It's very worth spending time looking at this derivation, probably even repeating the derivation a couple of times on your own after you've seen it here. So for phi of x, I just expand it in terms of this, and that's what I put in over here, formula 1, comma, and I put the commutator sign here, pi of y, and I put that over here. So every time I see an x here, I change it to y, which is this IPY and minus IPY. And each of these are summations, so technically this is a sum over p. because this is an independent summation, I just change the p to p prime and change this formula to p prime and y basically, and that's how I get this over here. Now this is just a commutator of two things, and each one of which has a sum of many terms. So whenever you do the commutator of a plus b with c plus d, you can just take the commutator of the individual terms. You can almost do a FOIL or FOIL like you would for that you may have learned in school, before college, like in grade school. First, outer, inner, last. You can do the same type of thing with the commutator. So that's what we do here. As we go down here, this whole thing, first we multiply out these constants, and you can pull that in front of commutators. So you get 1 over, this, apologize, should be a square root of v, over there. Those two square roots will just cancel each other. Well, just multiply to just v. So you have 1 over v. You have the square root of omega sub p taken from here, the square root of omega sub p taken over there, the square root of 2 here, square root of 2 here. That just gives us 2. So that can pull that out of the whole commutator formula because it's a constant, times this factor of minus I. Same thing, I can pull that out, minus I. And these two sums, the summation part, can be pulled out of the commutators. I just write it as a sum over p and the sum over p prime, or just sometimes I'll write it as a single sum. And then now I just have all the other terms in there. So I'm going to take the commutator of this term with this term, the first term here with the first term here, and that's the AP with AP prime. And these factors, again, because they're constant, can be pulled out in front. They're not operators. They're numbers, not operators, not constants. They're numbers, not operators. So I have e to the IPX, e to the IPY over here. Then for the next term, I go first, then I go this term with this term is what I did here. Then I'll do this term with this term. And here I get AP and AP and a dagger P prime. There's a P prime over here. It's kind of hidden over there. Let's put it over there. And then that minus sign will still be there because this is plus and this is minus. And then this exponential term can be pulled out in front, e to the IPX, e to the minus IP prime y. Then I'm going to do this term with this term, and that's what I get over here, a dagger P prime, or a no dagger P prime, the commutator of those two. Remember, this whole thing is a commutator, so I'm doing these independent commutators. E to the minus IPX, e to the plus IP prime y. It's taken from this with this. And then for the last term, I take this with this. There's a minus sign here, so minus a dagger P prime, commutator, e to the minus IPX, e to the minus IP prime y. And that's just this whole thing expanded. And ultimately, remember, I want to see that does this actually end up equaling I Dirac delta x comma y. Now, let's assume, remember we're doing a proof, but we want to assume if this is true, that we're going to actually show that this is true. If the commutation relations that I proposed on the previous page are true, in other words, if AP dagger is equal to 0 and a dagger, sorry, if AP prime is equal to 0, the commutator, and a dagger P prime commutator is equal to 0, then I want to start showing that we're going to get this. Well, if these things are true, then obviously this term will equal 0 because this is equal to 0, and this term will also equal to 0, so I can cross them out. And then I'm left with just these two terms. Now remember, I also, for the commutation relationships, also want to assume that AP comma AP, a dagger P prime is equal to this, Dirac, Kronecker delta P prime. So if I assume that, then these two terms will end up becoming the following. I still have this factor over here, which I say is 1 over 2v. The minus I pulled over here. This bracket I still pull over here. The summation I just happen to pull inside the bracket, doesn't matter here, over p and p prime. And then I'm going to take that summation for each of the individual terms. So now the only two terms are this and this. So for this term, I'm just keeping things here. I have the minus sign I pulled out in front, e to the plus IPX, e to the minus IP prime y, that's this over here. And now AP, a dagger P commutator is by assumption Dirac, Kronecker delta P comma P prime. That's what this is over here. This minus sign will get thrown out over here. sorry, I already pulled, yeah, this minus sign will be pulled out over here, and I'm pulling the summation on each individual part, so this thing is minus here as well. You can look at that more carefully. Sum over p prime, that sum I put out over here. E to the plus IPY, just swung these two around. E to the minus IP prime X, just taken from here. And now this over here is an A dagger P prime AP, which if you reverse that, you should just get minus the Dirac delta. And actually, that's where this minus sign comes from. So this minus sign stayed here. This minus I stayed over there. This plus became minus because this commutator is minus this commutator over here. Whenever you reverse the order of the operators in the commutator, you get a minus sign. This is minus delta P prime. So that's where that minus comes from. Sorry about that. So that's what I got so far over here for this expression, remember? We're going to continue this calculation on the next page. Just kind of reiterated everything we just put on the previous side right over here above the line. This is a repeat of everything above. And now I'm going to take a look at this term and just simplify it a little bit more. I have still 1 over 2v. There's a minus I. I'm going to make that minus here, and a minus here. I'm going to take this plus I and make these two terms plus. So this becomes plus, this becomes plus. This minus gets distributed out. And here, I'm going to actually apply now this summation of p prime, but also over this delta function of p and p prime. The delta function of p and p prime means that if p prime is not equal to p, then this whole thing is 0 and it kills this term. So this forces p to equal p prime. And this is what I get. Now I have, in other words, I do the summation. This is a double summation. You can even write that out like this. That, I have a summation over p and a summation over p prime. And now that summation over p prime is done. And then when I have the Dirac delta, that's automatically going to make every time p prime is not equal to p, in this double summation, that equals 0. So this forces in this expression p prime to equal p. This becomes 1, so it factors out. And now this p prime becomes p. So I have e to the ipx minus e to the ipy. Ip is common to both of this. And because they're exponentials, I can combine them into an exponential of a single term. So I have e to the ip and then x minus y. So that's what this becomes over here. And similarly with the second term, there's another Dirac delta over here. Remember, this minus became plus because the minus got applied. So, and then I just applied the sum over p prime. I'm not going to rewrite this here. And that forces p prime to equal p because of this Dirac delta. So I get this whole expression would just be e to the ip y minus x. P prime became p, and then there's y and minus x. So this is what I have so far. Now, remember from the mathematical interlude, the important thing that we assumed, that the sum of, that this term over here, the sum over p of e to the ip x minus y, is equal to v times the delta function of xy, this being the Kronecker delta function. Remember, we showed that in the mathematical interlude. So this entire expression would simply just become v dot Kronecker delta x comma y. And this entire expression will become v dot Kronecker delta x comma y. Same thing over here. And these two things would be the same. The delta function of x comma y is the same as y comma x. So I could just put that over here. So now these two terms are identical, so I can combine them to get two of them, 2v delta x comma y. And then the two v's will cancel. And as my final result, I get exactly what we wanted, I delta x comma y. So in other words, this commutation relation is guaranteed if the commutation relations for the A and A daggers are as we stated. So that verifies the proof, at least in this direction. I'm not going to show the other direction, but if you start looking at these things and playing around with it a little more, you can also show that. But this should be pretty convincing. You can also derive exactly the same thing in the continuous form if you use David Tong's expansions as continuous expansions for phi and pi. We used Klauber type one before, and the discrete form. And if you assume this as a commutation relationship instead of just equals the regular delta function pp prime, you have Dirac delta function and also a factor of 2 pi to the third, then you can show the same thing. I'm not going to go through this in this lecture, but these slides are pretty thorough, so you can take a good look at them and see why this is true in this continuous form. And I think it's worth probably proving it. Good practice. This continues that as well and shows the same thing. These are really derived from David Tong. If you want to look at the lecture notes, has wonderful lecture notes on this derivation also. I might have a couple more steps spelled out in between than he did. So now we did a very important thing where we found out that the commutation relations of phi and pi, being naturally derived from quantum mechanics, forces us to have new commutation relations between these other operators, A and A daggers, as we've talked about. And that's going to be very, very, very helpful. Instead of dealing with phi and pi, even though that physically gives us the best picture of what's going on with these balls on a 1D track, which I think you still should have for a physical picture, our mathematical trick is to kind of re-express things in terms of A and A daggers, and those commutation relations will make life a lot easier. So our ultimate goal right now is to re-express the Hamiltonian, which we have very well explained in terms of phi and pi from all the previous lectures, in terms of AP and AP daggers. And we did a similar thing with the simple harmonic oscillator. Now we're going to do it for QFT. You will recall, this is again our formula in the discrete form. Our expansion for phi is this over here. Our expansion for pi is this over here. And remember, this is the Hamiltonian that we were dealing with all along. This is the Hamiltonian density, and the integral of that d third x gives us this. And I pulled out the factor of a half here. So I am just going to plug and chug and be very careful with a lot of little factors and sums and summations and Dirac deltas and things like that, or Kronecker deltas. But we're going to plug these formulas into here. And at one point, we will also take the derivative, the gradient of phi over here, which is the derivative with respect to x, the derivative with respect to y, the derivative with respect to z. But we can kind of have simple formulas for that as well. And we'll take a dot product of this. So let's do that. So step by step, we first have pi squared. Here's our factor over here that's out in front. So we're going to square this thing, which is the expansion over here. It gets very tedious. So quantum field theory, if you just stand back and walk at these pages, everybody gets intimidated. But everything in math is really built out of lots of small, simple steps. It's like a Lego piece. If you just stand and look at the final Lego piece, it seems impossible, but every single part was step by step building up the more complicated things. So I hope you don't get intimidated. Just take a look at this. Is just a natural expansion. Here's pi of x right over here, and same thing right over here. I just put the same thing in twice because it's a summation over p here and a different summation over p here. I just changed the p to p prime. So that's what this is, this guy. Then the last term, the m squared phi squared, here's my m squared. I just do exactly the same thing. I take this expression over here, put it in twice, this times itself, and I change the p to p prime in the second summation just so that we can keep track of where these p's are coming from. That's all that is. And then to figure out the third term, I first have to remember to take the derivative of this, technically the gradient of that, and that's almost exactly what you think. You can play that around with vector calculus ideas a little bit, but basically that's exactly what this is. The del phi, the gradient of phi is just really, I just take the derivative of this. I still keep the factor 1 over square root of v, 1 over square root of 2 omega p, and then this ip, because I'm taking the derivative really with respect to spatial coordinates, gets pulled down. It's a vector. If I just put that as a vector, I don't have to think about all three coordinates independently. You can look at a book on this or just take your time and rederive it if you want to go x, y, and z separately. But this whole thing, remember, will ultimately give us a three-dimensional vector because, or the equivalent of a three-dimensional vector. It's really an operator, a three vectors operator. So that IP will get pulled down over here. And I have AP here, e to the plus IPX over here. So it's basically the derivative of a constant and the derivative of this, which gives me the same thing, but with respect to x. So the IP part gets pulled forward over here. And similarly with this derivative applied to over here, I have a minus IP, so that this minus IP gets pulled over here, and I still have an A dagger P, which doesn't get changed, and this original term, e to the minus IPX. So that's what this is over here. So I'm going to throw that in here and dot it with itself, because technically this is kind of a 3-vector of operators, and that's going to be dotted with another 3-vector of operators. So that's what all this term is over here. This thing here, applied here, and dotted with itself. And I just have a p prime here again to keep track of the different independent summations. So that's this expansion for h that I have so far. Hopefully you're following along with me. I can still condense things down a little bit more, which is what this is over here. If I kind of expand each of these terms, this is what I'll get. I'll take this 1 over square root of v, 1 over square root of v, and just get 1 over v. I have a factor of minus I times minus I, which will give me plus I squared, which is minus 1. That's where this minus 1 comes from. I have a square root of omega p here, and a square root of omega p prime over here. And on the bottom, I have a square root of 2, square root of 2, and that just gives me 2 on the denominator. That's what this part is so far. I'm just multiplying these whole two things together. Then I pulled out all those constant factors in front, and then I just have this thing times this thing, which is what I wrote here. This thing here times this whole thing over here, and that covers this whole first line. The second line is the same kind of math. You can take a look at it. 1 over square root of v, 1 over square root of v, I get 1 over v. I have a similar thing with an I here and I here that can get pulled out, I here that can get pulled out, and that's I times I, which is I squared, which is a negative 1, which is right over here. Then I have these other, I have the negative 1, which is over here, and then I have these other square root of 2, which is just 2, and the square root of omega p, and the square root of omega p prime right over here. Then these p's can get pulled out, so I can pull out p from here, factor it out, and I could pull out a p from here and factor that out, a p prime from here and factor that out. And if I dot the two together, I'll just get the dot product over here. This dot product ultimately would just get translated to this over here, so I don't have to worry about it while I'm doing the rest of this expression. I have the dot product of the vector p dotted with p prime. That comes from this dotted with this. And now I finally can just take this and just write these remaining two terms together. So this term over here is this term right over here. And that's multiplied, not even dotted, by this second part over here. This over here minus this over here. And the same thing with the third line. I can do exactly the same thing, pull out the v's, I get 1 over v, m squared over here, 1 over 2, 1 over omega sub p, 1 over the square root of omega sub p, and the square root of omega p prime, omega sub p prime. And then this thing is over here, and this guy is over here. So that's that expansion over here. You should take time and look at this and make sure that it makes sense. These kinds of calculations happen over and over again in quantum field theory. They're not easy, they're not hard either, they're just very tedious. So make sure you keep track of things. This is just that whole thing repeated since we ran out of space over there. So now is where we come to some important things that are based on our mathematical interlude. Remember the formulas that we came up with were this, and we showed very clearly why in the mathematical interlude, that the integral of d third x of e to the I p plus p prime dot x gives me this, equals v times the Kronecker delta of p comma negative p prime. And the same type of thing here with delta, with this expansion over here, I get v delta p comma p prime. Now, what's so good about that? Well, now let's look at this expression over here. Remember, I have this whole thing over an integral of d third x. So I can rewrite, I'll just focus for now on the first term over here, this whole kind of like first line over here, and rewrite it in this way. We'll get to the second and third lines on the other page, but let's just look at that first term over here. Here's my, we'll just make sure everything makes sense here. 1/2 gets pulled out here. Here's my summation over p, my summation over p prime. Minus 1 over v is here. The square root of omega p, square root of omega p prime are here. Over 2 is still here. Then I look at these parts over here, and I go ahead and I do my FOIL, like, you know, when you multiply two binomial terms together, first, outer, inner, last. So I can do that. So the way I do it kind of consistently with this is I'll take this term multiplied by this term, which is over here. This term multiplied by this is AP prime. And then I have this term, e to the I px, and this term, e to the I p prime x. Now this x is the same among both of these, so I can factor it like this, to e to the I p plus p prime. And where does this integral come from? Remember, the whole thing is integrated over x. This is all like Hamiltonian density stuff, and the whole thing was integrated over d third x. So now I can distribute that out to every one of these terms if I want. And because it's a d third x, and all of this stuff here, including this right here, has nothing to do with x, it has only to do with constants and p prime, I can now take that integral and swing it all the way through and just do that integral, because none of this stuff has to do with x, so technically they're constant, they get pulled out of it. And I can just take this integral over d third x and apply it to this part here, which does depend on x. Again, we're looking at the first term. I could do the same thing. I remember I take this term times this term. Now right over here, I'll take this term, the first term times the last term over here. And that gives me my a dagger p prime. And now the integral over this thing here will be p minus p prime x in the same way. That minus sign will be here because of this. Then I do this term times this term. I get another minus sign over here. A dagger p, a p prime, no dagger. And then the integral over d third x, which is distributed out over this exponential, e to the minus I px, and e to the plus I px, and the minus and minus, e to the plus I p prime x, and the minus would technically reproduce this over here. Okay, so take a look at that. And then the last term is this with this, so that minus and minus gives me a plus, and I get an a dagger p and a dagger p prime over here. And then the integral d third x over e to the minus I p x, and then e to the minus I p prime x, which is just, that's why I have p plus p, so that will become minus, if you distribute out the minus, you get minus I p prime x. So this whole first line is this over here. What's so important about expressing it like that? Well, now we'll use our two things that we wrote up here that were derived very clearly in the mathematical interlude. So this term here should remind you of these terms here, all of these terms, and there's analogous forms for them. And I'm just going to apply this formula over here. So in other words, I'm going to change this for the delta functions. So I just rewrote this whole thing here, but every time I see this integral, I just changed it to v times the delta function for this, which is the delta function of p comma minus p prime. And this, the way when I write it, this, remember this is Kronecker delta, not Dirac delta. And I just do the same thing with every term. See this term over here? I just rewrote this thing in terms of the delta function. Same thing with this over here with this term, and the same thing with this term over here. Rewrote that as the delta function, and if you look carefully, this is what I should get. Now we're getting there. Now I'm going to use these delta functions and do this summation over p prime for all of these terms. And once I apply the delta function, remember this is the sum over p prime for here, the sum over p prime here, the sum over p prime here, the sum over p prime here. I could distribute out that p prime. First, just housekeeping order. There's a v in every term here, and there's a 1 over v before it as a prefactor, so that will cancel. But now once I apply the delta function of over p prime over here, once I do the summation over p prime and use this delta function, this delta function forces p prime to equal negative p, because there's a negative sign here. So when I do that expansion, I will get ap and a negative p. That's how this comes negative, because the p prime has to be negative for this first term here. And I'll show you for the rest of the terms here before I get to the WP part. This Dirac delta says p and p prime are the same, so this p prime stays as p, just regular p. So this p prime becomes regular p. Over here, that minus sign still stays. If you look at this term over here, same thing. This minus sign stays. I have a dagger. This p stays, and this p prime just becomes regular p because of this Dirac delta, because of this Kronecker delta. I'll just keep saying that. And then this over here is a dagger p and a dagger negative p, because there's a negative on this Kronecker delta. So that's how this whole thing shakes out over here. Now, what about the WP prime part? Well, there you have to be a little bit careful when I do things like this Dirac delta. That's also going to force inside this summation this WP prime to just be WP, and the square root of WP times the square root of WP just gives me WP, which is where this comes from here. This minus sign is still derived from way back here, as this 1/2 comes from here, this 2 comes from here. So that's why that happens. But what about here? Because technically, if you did that same thing here, this would be WP and W of negative P. when p prime, because p prime would be forced to be negative p. So how does that work? Well, that's where you just have to look at the definition, and this is so far just a definition. I'm not telling you yet what WP is. When you do WP, which I'm calling W is really omega p, that actually has to remember the definition of WP or omega p is equal to the square root of p squared plus m squared. But if you did W of negative p over here, if you plug that into that formula, you should get this, negative p, the whole quantity squared plus m squared. But a negative number squared is just the same thing, positive, p squared. So negative p quantity squared is just p squared. So these two actually end up being the same thing. So anytime you see a omega negative p or W negative p, which should really happen here, you can convert that to a regular omega p, and that matches this term. So then every one of these things, whether they have just p and p prime on the delta, or on the delta, or p and negative p prime, will end up for this part over here not affecting it. It affects these parts, but it won't affect this part. So this will still be omega p times omega p, which is just the square root of those two times each other is just omega p. Square root of omega p times square root of omega p should just give you omega p over here. So a lot of stuff here, but this is just our first term, and this is what we get over here. We can do similar types of things with our other terms. So I just kind of spun things around here. The first term is on the previous slide, and I'll put that in a moment. Let's now look at our second and third terms. So the second term is the second line, or whatever you want to call it here, is this thing underlined in green. And I have that over here. And by exactly the same arguments, you should get this. You have to be a little bit careful here. I could go through a little bit here, just maybe one or two lines, but you can take a good look at this, but you should get exactly this. That, here, here's my factor of 1/2. It's over here. The v factors will ultimately cancel out for the reasons I showed you before by remembering these relationships. And then the omega p prime will end up, omega p prime will end up being omega p. And those two things, the square root times the square root, just gives you omega p, and this 1/2 is over here. For these parts over here, you will just do the same type of thing, a FOIL, AP and AP and AP prime. And then you'll get AP and AP prime, but then you'll have e to the IPX and e to the IP prime x. And if you combine those, you get I to the P plus P prime x. And then if you take this original integral over d third and apply it to this, you're going to use this relationship over here, the integral of d third x over e to the I p plus p prime of x, and you get v times this delta function p minus p prime. So just take your time and go through this. It's exactly what we showed on the other slide, but it's worth doing it again because it is kind of tricky. Here you have to be careful. You have a p dotted with the p prime, and if you have a situation where you get a delta function with the p and a negative p prime, you have to remember to turn this to a negative p. It's going to force p prime to equal negative p, and in those terms you get this negative sign over here. So if you do all that here carefully, and you should do it, you will get this over here. We did it all on the previous slide for the first term. This is just the same thing for the third term. Sorry, for the second term. This is for the second term, the one underlined in green. The third term is now right over here, and I kind of have it outlined right over there. If you take your time and do it, you should get this over here. So this, and then if I apply what we did on the previous slide for the first term, which we already calculated, this so far the final expression that we have for the Hamiltonian in terms of A's and A daggers is this over here. We'll keep grinding out some more on the next one, so I just kind of reproduced that up here since we ran out of space on the previous one. So everything above the dotted line we've already derived. Now looking at this over here, we can expand this even better. So this is a sum plus a sum plus a sum. So if we expand everything out, we can kind of reorganize the terms. If we just focus on the terms like this, we notice on this first line there's an AP and an A minus P here, here, and here. So if I kind of reorganize how I sum this, I have that over here, AP and an A minus P. And then I just look at the things that we're multiplying it. Here I have a P squared over an omega P. I took the 1/2, which is in every one of these, and I pull it out. So I have 1/2 originally, then another 1/2 over there, which counts for these twos. You don't have to think about them anymore. But this one over here is P squared over omega P. plus this term over here, which is just still the m squared over omega p. That m squared is still there. And then this part over here is minus omega p. And that, remember, that 2 is still pulled out over here. So that takes care of these three, are reorganized right over here. Do the same thing with these three. All three of these are AP, A dagger P, here, here, and here. So I'm just going to pull that out and then factor that out from all three of these, and then just look at the other terms. So this part over here is P squared over omega P. This one here is just M squared over omega P. And then this one here is just negative and negative. So this is a minus sign that technically can be distributed out to each of these. So negative and negative, so which is just plus omega p. And that 2, remember, just gets pulled out over here. So that accounts for this over here. That's what I get so far. I'll do the same thing now for this line. A dagger p, p, here, here, and here. I pull that out of these three. And here's the factors, p squared over omega p. And this one here is m squared over omega p. And this one here is negative and negative, so which is just plus omega p. And the same thing on the last one over here. Just pull that factor out over here. A dagger p, A dagger negative p, and then I get p squared over omega p plus m squared over omega p plus, or minus here, minus omega p. So again, seems tedious. You should spend time and try to do these calculations. It's good practice. It gives you like a skill. It seems like harder to describe in words. I tried to color code it here, so this might actually help you with a lot of the derivations and kind of go through it mostly step by step. I'm going to keep grinding out over here. Remember, I'm just still trying to re-express my Hamiltonian in terms of A and A daggers, and I've already done that, but I want to show you that it will simplify out a lot more into a very beautiful formula. So all I'm going to do from here to here is just factor out. I notice that there's an omega p all over the place. I'm going to factor that out of everything. So I'm going to do 1 out of omega p pulled out of every one of these terms here. So the rest of it stays the same, but I just factored out the 1 over omega p, so that's out of here already. So just I'm left with p squared. I factored out the omega p over here, that just left with m squared. And here, since I factored out omega p, I have to make this omega p squared, because omega p squared over omega p will just give me my omega p. And these plus and minus signs stay the same. I did the same thing over here, factor out the omega p, factor out the omega p, and then this omega p just becomes omega p squared. Same thing over here on this line. This omega p's are all factored out. And same thing over here, the omega p's are all factored out. So now take a look at this expression, which is what we have right now. And you will recall, hopefully, that we just defined, without explaining what it means yet, that omega p squared is equal to p squared plus m squared. That's by definition. So that means that p squared plus m squared minus omega p squared has to equal 0, just based on simple algebra. But take a look. We have two areas here and here where we see exactly this expression. So both of those are equal to 0. So these two terms get knocked out altogether. And our Hamiltonian is now this plus this. And we crank out further. This is just what we have from the previous slide so far, once we got rid of those two terms. Now we will use the commutation relations, which we spent a lot of time deriving just a little bit ago, that AP comma A dagger P prime is equal to delta of P comma P prime, right over here. Well, that obviously means that by definition of the commutator, that AP, A dagger P minus AP, A dagger P, AP equals 1. That's the definition. This part's the definition of the commutator, and that just equals 1 when we have P equals P prime, which is the situation here, because this was just P prime. So this P prime equals P, which is what we have here. It gives us 1 for this delta function, so that's what this is. And then you can just rearrange things here to this to say that AP, A dagger P, is equal to 1 plus A dagger P, AP. And what that means is that every time we see this in AP, A dagger P, which we see right over here, for example, we can rewrite that as this, since these two are equal. And that's what I've done here. I take this whole thing and rewrite just this part over here, using this formula over here as 1 plus A dagger P, AP. And I get this line over here. Now we just expand things out. 1/2, 1/2, 1 over omega p, sum over p still stays. And I can just now expand things a little bit. So I have 1 times this factor over here, which is p squared plus m squared plus omega p squared. That's just the 1 over here. Plus, then I have an a dagger p, AP, and then this whole thing, p squared plus m squared plus omega p squared. So this and this. But then I also have that exact same thing here, a dagger p, AP, and then the same factor here, p squared plus m squared plus omega p squared. So I have this once and this again, and that's just 2. One of these plus another one of these gives me 2 of these. So I have 2 p squared plus m squared plus omega p squared, a dagger p, a p. That's what I got here so far for the Hamiltonian. Now just remember again that we talked about omega p squared equals p squared plus m squared. So if you just expand that out, you have 2 p squared plus m squareds, or just 2 omega p squared, because this whole thing equals this. That's the definition of omega p. And the same thing applies here. So this becomes 2 omega p, 2 omega p. And now if you just keep cranking it out, you get the sum over p, which I just pulled out here, a half, 1 over omega p, 2 omega p squareds, right over here, plus, and I just factored this whole thing out again, a half, 1 over omega p, 2 goes over here, and then 2 of these, 2 omega p squareds, and then a dagger p, p comes right over here. So this number here and this thing over here with these operators attached to it. Just keep cranking it out. All these 2's are going to cancel. This will cancel. These 2 will cancel these 2's. This omega p will cancel 1 of the omega p's there. Just leave this with an omega p. This omega p also, same thing, will cancel 1 of those over there. And after you crank it all out, this is our very important formula that we get for our Hamiltonian. This is our Hamiltonian, which we started with the very cool expression in phi and pi that we derived based on things like special relativity and all that, applied to a classical scalar field and normally extended to quantum field theory. And instead of solving the Hamiltonian directly in the phi basis, which we could, and gives us a more intuitive picture in terms of balls moving on 1D track all over space, we simplified our problem by changing our by redefining things in terms of a and a daggers. We re-express phi and pi in terms of a and a daggers, and we just showed that if we do that, we get this pretty simple formula for the Hamiltonian. The Hamiltonian is equal to the sum over p of omega p, a dagger p, AP, plus the sum over p of 1/2 omega p. We're going to analyze this a lot more in the next lecture, but a couple of things I want to just go over right now before we get to the next lecture. We'll find what the heck was the point of all this. We'll find that this way of expressing the Hamiltonian is very helpful and tells us almost immediately what are the eigenstates and the eigenvalues. Just like in the simple harmonic oscillator, we have a sum here. Remember, in the simple harmonic oscillator, we noticed a very similar thing, that if we simplify it, it becomes a lot easier. If we didn't, we tried to express it in the x basis, we had Hermite polynomials. The problem could be solved, but got a lot more complicated and somewhat hard to interpret. But we're going to find that this is going to be very simple. Before we get to that, notice the Hamiltonian is this plus this term over here, which we do get in the simple harmonic oscillator, but there's a potential problem with this term here. It's talked about in a lot of different books, and you can spend a lot of time reading about it. I wouldn't say I'm an expert at it, but let me tell you a little bit about what I know and what I've learned. This is called like one of the infinity problems and its solutions. So let's look at this second term. Forget this for a moment. We have the sum over p of 1/2 omega p, and omega p is p squared plus m squared. And p's, we talked about what are the allowable p's in our system. Remember, we've mentioned that many times. So if you let p itself be even these discrete multiples, but go from all the negative values all to all the positive values, even in discrete steps, well, then p squared plus m squared, which is a positive number, times a half, which is still a half of a positive number, is still a positive number, will end up just giving you infinity, because you're going to keep adding all these positive numbers together, even as you go range through all of p's, even if they're discrete. However, we talked about, at least I am doing it, and maybe controversial, but I am actually restricting p to 2 things. One, the quote-unquote complete cycle values, like we've talked about a lot in the mathematical interludes. But also, I made a statement before that I want the total number of p terms to equal the total number of voxels in our system. I assume if we're in a finite system, we have a finite number of voxels, that they're not infinitesimally small. and there's space is not infinitely big, so that gives us a finite number of voxels. And just like is done in condensed matter physics in the Brillouin zones, for those that are familiar with it, I'm saying the number of p terms is equal to the number of voxels. That's somewhat of a controversial assumption, but there's a reason I gave for that in the mathematical interlude that you can look back and check out. It won't ultimately matter that much, but I think it helps us clarify things the way that I find a little more satisfying. So if that's the case, it doesn't give us infinity. It still gives us a pretty huge number because p is not allowed to go to the highest positive integer, integer multiple values, and same with the negative. It has to stay bounded from above and below, in addition to being discretized. So technically, we'll get a large but finite number here. Could that still cause problems in our calculation? Potentially. It just says that at the baseline, you have some huge energy that you're going to get. Remember, this is ultimately going to represent the energy of our system. And if you just throw a huge constant number there, it's going to add to the energy eigenvalues that are possible, infinity or at least a large number. But it turns out, at least if you look at all these quantum field theory books and talk to experimental physicists, and I'll get to a little bit of this. I'm not an experimental, I'm not a physicist, I'm an orthopedic surgeon, and I haven't read that much on experimental physics and haven't found great sources on it. But basically, what is very clearly stated, which I mostly know why, and you probably also know why, is that when you measure things, we like to think we're measuring the absolute energy, but generally speaking, whenever you do any kind of measurement, the only thing you can really do is measure the difference in energies. Like you start in one energy state and you jump to another energy state, and you just technically know the difference because you may have absorbed a photon, for example, or emitted a photon. So all you can really tell is not the absolute value of the energy of the first or second state, but the difference in the two energies. And if that's the case, this is just a constant number. It's a big number that will just be added to every single eigenstate. We haven't gotten to yet the eigenstates yet. We'll do that in the next lecture. It'll be a lot easier once we have this form. It's actually pretty easy. But what we'll show is that we have to add to every single energy eigenstate. The eigenvalue of every single energy state will just be added to exactly the same constant number. And that constant number basically won't be seen in any experiment because you're just looking at energy differences. That's pretty much our cop-out and how we get rid of this infinity. There's other interesting talks which I don't know much about, and you can look at David Tong's note on things like the vacuum energy and the Casimir effect, which might actually measure the energy in an absolute fashion, but I won't get into that because I don't know much about it. We're just going to move forward on what I know more about quantum field theory. There's some even questions in general relativity about these types of things as well. The energy density of absolute space, of space itself, should have some effects on curvature of space-time and things like that, but that's getting beyond what I understand and what I'm going to cover in this course for sure. But interestingly, if you cut off p in that way, you get a very large number, still but finite. And then if you use this argument, which is a great argument for quantum field theory experiments, that you only measure energy differences, you pretty much don't have to worry about that. There's another argument that's used often, which is problematic, but used often. I think you can read about this in Klauber, where he talks about, well, David Tong talks about this as well and gives a little bit better justification for it, but there's something called normal ordering. I'm not going to spend a lot of time on that now. I'm going to get a lot more into that later. But basically, normal ordering means this, that if you have an operator like AP and A dagger Q, we haven't gotten to it, so I don't want to ruin the surprise over here, but what normal ordering means is that anytime you have a non-dagger term, which will later on be called the destruction operator, but I haven't gotten to that yet. You may know a little bit or hint that if you pay attention to our simple harmonic oscillator formula and argument and discussion. But what normal ordering means that just arbitrarily, if you normal order two operators that are kind of multiplied together, you just force the operator that is not daggered all the way to the right. So you just force that. So that if you have the normal order of these two, you just force it this way. If you did that and you look back at our derivation for this Hamiltonian in this form, at one point in the derivation we had this, and if you normal order this, just arbitrarily forcing the Hamiltonian to be normal ordered, not for great reason or argument, just saying some reason I have to normal order it at this step, then you'll see that this will naturally turn into this, and then you lose that extra constant term, and you will just get this formula for the Hamiltonian. It gets rid of that extra quote-unquote infinity term. At any rate, regardless of the reason, for all the reasons that we said, This is our final, very important form for our Hamiltonian that we've now re-expressed in terms of A and A daggers. So it's this. We got rid of that infinity term. This is the discrete form, like that you will see, for example, in Klauber's book. And this is the continuous form that you'll see in David Tong's notes. The 2 pi to the third comes in because of his convention, as we've talked about before. And that's it. We're going to find out that these forms allow us to really powerfully solve the problem in quantum field theory that we have so far for our scalar theory, to figure out what the eigenstates and eigenvalues are, and they'll have a very beautiful interpretation in terms of things, in terms of particle states. That's it.